I'll talk about CMOS characteristic in device physics. Okay, here is CMOS inverter. Here, this operates like a green light, white light, like a PMOS operate, and MOS will off, and if MOS operated and PMOS is off. So this is the graph diagram with PMOS and MOS operate like this. So here is NMOS will be off, and here it will be PMOS off. No, it's reverse. NMOS will off and PMOS will off. So one is here. So here is PMOS will on and NMOS will off. Here is number two is here. So NMOS will linear region and PMOS will saturation region, and 3 is here. So both the MOSFET will saturation mode, and here is number five will be MOS will saturation and PMOS will be off. So it will be match of the velocity, operate velocity. So but carrier mobility is different because hole and electron will have different energy and different polarity and different so we have to match the ID saturation by width and length. So when long channel PMOS width and MOS width is very many difference. Width of PMOS will be very large, so some 2.3 is here, but in short length there will be 1.3 is very small. So very small difference in width of PMOS and MOS, because in short channel very small, and mobility is very small. So no difference in short channel. And mobility is down, and ID saturation is down, and in Ohm's law, resistance is high when I is down, current is down. So and tau is RC, so tau will be larger. So tau is delay, so delay is larger in short channel than long channel. And this is the VDS, ID VDS of MFET and PFET. In low VDS, there will be MFET is to 1.2 milliampere, and PFET will be 1 milliampere in 0.5 VDS. It seems like a when we match the ID saturation with PMOS and NMOS, but this is only saturation level. We have to know about linear region. In linear region, it can difference when even if we match the ID saturation. So and when operate the MOS and PMOS, it will be have a time delay. So this is the delay of the operation. So this is the falling delay and this is rising delay. 시끄러워도 돼. 교수님 신경 안 써. 막 술집에서 해도 된댔어.
진짜?
So this is graph of the VDD to the ID VDD, and red one is PMOS and blue one is NMOS. So we talk about power dissipation, dynamic power dissipation. Power P is IV, so I is dq dt, so P dt, so dt time dt is, so integral P dt is I integral V dq, so integral V dq is QV. QV is the capacitance, so PT QV is PTQ and QV CV. So P is CLVDD square over tau. Frequency is tau of lattice. So P is CLVDD square, frequency F. This is the dynamic power dissipation. And T dynamic delay of time is standard is half of VDD. So VT delay, total delay is average of TDT, TDF and TDR. So delta Q is CL and half VDD, and Q is the integral of ID saturation dt. So TDF is CLVDD over 2 ID saturation N, and TDR is CLVDD over T ID saturation P. So we have to go to average of total TD, so T. And fan out is here. Fan out is here. This is one output to several input of several gates, but too much input to one output, it'll be very larger. It will be larger capacitance, load capacitance, so more delay to output. So here is the graph. This is the slope of R, and if one output is here, two output is here, three outputs here, more output to more delay. Okay, this CMOS is here, and we have to talk about short channel effect. first effect is 80 months to two times of integrated, and more integrated circuit is more smaller die is more economy, more efficiency to make semiconductor, because one wafer is one wafer to more die. Okay. So first is punch through. Punch through is the connect of the depletion, not the channel. So this is not expected effect, also bad effect. This is why in source and drain is N plus semiconductor and body is P substrate, so P plus. So there is this depletion region between source, drain, and P sub, but in drain more plus bias is made more depletion region, so more and more, so larger depletion region. And this circumstance, very little gate bias can connect the depletion, so it can make a channel. So this is the lower than VT, so lower VDD and more IDD in off circumstance. So sub-threshold swing is larger. So this is the graph of the punch through. So very shorter gain length, 5 micro, 3 micro, 2 micro, and 1.2 micro, 1 micro, and 0.8 micro. Shorter length will very loose slope. It can say poor sub-threshold swing. And here is the VT of the slope change, and lower VT is here. We can see the lower VT to shorter gate length, and we can see the punch through to energy band gap. So this is the ideal energy band, and this is the punch through energy band. Here is very poor station, poor region. This is a solution.